Hello and welcome to another exciting Everyday Chemistry laboratory video. Today's experiment is entitled Electrochemistry. Electrochemistry is an extremely important application of chemistry to everyday life. Think of how every person on Earth practically is carrying a cell phone of some sort with a battery in it. That battery, that lithium-ion battery, is a product of chemistry. In fact, it's a product of hundreds of years of chemistry. Back in the turn into the 18th century, when Galvani discovered something called animal electricity, where two pieces of metal stuck into a frog's leg would cause the frog's leg to twitch in an electrical storm. Soon after that, another famous Italian scientist named Alessandro Volta invented the voltaic pile, what we now know to be a battery, where he took two pieces of dissimilar metals, like zinc and copper, and separated them by a salt solution and found that those pieces of metal produced an electric current. So today we're going to construct a few simple batteries as well as discuss some of the other implications of electrochemistry. In procedure 2A1, we're going to look at the reaction of 5 different metals with hydrochloric acid. And this is an illustration of the metal activity series, where certain metals will replace other metals in chemical compounds. And this has implications for constructing batteries as well. And in the laboratory write-up, there's a discussion of activity series and metal replacement. So let's start with copper, and then we'll work through aluminum, zinc, tin, and magnesium. So I have 5 small test tubes containing 1 molar hydrochloric acid. And into the first test tube, I'm going to put a small piece of metallic copper. And we'll observe what happens when I do that. And if you look closely, you can see basically that nothing happens. The copper is sitting at the bottom of the test tube. Next, we will try a small piece of metallic tin. Putting the tin in the test tube, if you look closely at the test tube, you can see that the tin is forming a few small bubbles. Difficult to see perhaps on camera, but the observation is a few small bubbles appearing very slowly. Next metal we'll try is zinc. So after placing the piece of zinc into the hydrochloric acid, one could observe a much more vigorous reaction, vigorous bubbling and production of hydrogen gas. The next metal we will try will be aluminum. Now, aluminum is an issue because although it is a fairly reactive metal, it does form a hard oxide coating which can prevent its exposure to the hydrochloric acid. So if I put a little bit of aluminum in, why don't we just let it sit there for a minute or two to see if it starts to react. And in the meantime, we'll do the one that should give a very vigorous reaction, and that is magnesium, because it is the most active metal in the series. And putting magnesium in the hydrochloric acid, you can see quite a vigorous reaction. Vigorous, bubbling, producing hydrogen gas at a high rate. Very exciting. Meanwhile, our aluminum is sitting at the bottom of the test tube, not doing too much. So for that observation, I guess you'd put down very little reaction. So for zinc, moderate reaction, copper, no reaction, tin, very little reaction, magnesium, vigorous reaction, and aluminum, very slight reaction. So in procedure 2A2, we're going to explore the activity series of these 5 metals. So I'm going to start with really 4 test tubes containing zinc nitrate, and we're going to add each of copper, tin, aluminum, and magnesium to these test tubes to see whether those metals will replace zinc in its zinc nitrate salt. So starting with tin, I'm going to take a small piece of tin metal again and place it into the test tube containing the zinc nitrate. And as you can see, hopefully, there is no reaction. The tin is sitting at the bottom of the test tube with no apparent change. Next, we're going to take a piece of copper and put it into a zinc nitrate solution. After some amount of time, we can see again that the copper is lying at the bottom of the test tube unchanged. So copper is not replacing zinc. Next metal to try will be aluminum. So we put a piece of aluminum in the test tube containing the zinc nitrate. Let that sit for a few minutes. There is really no apparent change. And finally, if we take a piece of magnesium metal and put it into the test tube of zinc, we can observe that there is a reaction occurring, and the magnesium appears to be dissolving. I realize you can't see this too well on the video, but take my word for it. The magnesium is dissolving, and it's producing a little bit of mossy zinc on the bottom of the test tube. Next, we're going to test a solution of copper sulfate. And into each one of these test tubes, we're going to place each one of these metals except for copper. So the first one will be tin. So placing a small piece of tin into a test tube containing copper sulfate, we're going to let that sit there for a minute as we do the other metals. So then we're going to take a piece of zinc and similarly place it into a test tube of copper sulfate. We're going to let that sit momentarily, and then we're going to do the same thing with aluminum and with magnesium, dropping magnesium as I go along. So first, the tin is dissolving a little bit and forming a coating of metallic copper, that red-colored metal on the surface. The zinc has formed a nice layer of copper. Just pull the zinc out. Maybe I could show it to you up close. The zinc has gone from being a shiny white metal to basically a metal coated with metallic spongy copper. Then with the aluminum, again, there is no apparent reaction, although the aluminum certainly should replace the copper. Again, that's due to this hard oxide coating on the aluminum. And finally, magnesium, which has dissolved completely and formed a layer of mossy copper on the bottom. So in this part of the experiment, we can say that tin is replacing copper, zinc is replacing copper, aluminum should replace copper, but it didn't, so the observation is that it didn't really, and finally magnesium replaced copper with vigor. Next up to test is magnesium nitrate. We're going to put a sample of each metal except for magnesium into each small test tube and observe what happens. So copper, tin, zinc, and aluminum. So after letting each one of these sit for a minute, 5 minutes or so, carefully looking at the bottom of each test tube, I will tell you that nothing has happened in either one. So none of these metals, neither copper, tin, zinc, nor aluminum, has replaced magnesium from its salt magnesium nitrate. Next up to test is aluminum, and we're going to place each one of these metals into a solution of, in this case, aluminum sulfate. So again, the copper, come on copper, the tin, copper is trying to get away on us, the zinc, and the magnesium. So, copper, no reaction. Tin, no reaction. Zinc, no reaction. And the magnesium appears to be dissolving slightly. So we do have a reaction with magnesium. So we can conclude that magnesium does replace aluminum from its salts, but none of the other metals does. Finally, we're going to test tin chloride and place into test tubes containing tin chloride some copper, some zinc, some aluminum, and some magnesium. And after about 5 minutes, I observe that the copper is undergoing no reaction, so that's not replacing the tin. The zinc is dissolving, so it seems to be replacing the tin from tin chloride. The aluminum similarly seems to be dissolving, so it's also forming a coating of tin on its surface. And the magnesium, again, is reacting very vigorously, replacing the tin. So apparently, tin is replaced by zinc, aluminum, and magnesium, but not by copper. In the next part of the experiment, procedure 2B, we're going to construct some galvanic cells, which really are batteries. So we need 2 electrodes to construct a battery, and we're going to use each one of our metals in combination with each other one to make a battery, and then we're going to test the voltage that that battery is producing. So to do so, I'm going to take a spot plate with wells on it, put, for example, some magnesium nitrate in one well, and in the adjacent well put some, let's say, zinc nitrate. Then we're going to connect those 2 wells with what is called a salt bridge, which is a piece of filter paper that's soaked in potassium nitrate and serves to complete the electrical circuit. That is, we would have the flow of charge through the solution of potassium nitrate that's soaked up into the paper, and then into each of the wells, respectively, a magnesium electrode into the magnesium solution, and a zinc electrode into the zinc solution, and then we're going to measure the voltage that's produced. So let me try to set the camera to close-up to see what we get. Okay, so we have 2 well plates here that I'm putting zinc nitrate into one of them. And magnesium nitrate into the other one of them. Then I'm going to connect the 2 wells with a piece of potassium nitrate soaked paper. So we have magnesium on one electrode and zinc on the other. And if I dip the electrodes connected to a voltmeter into the respective solutions, we can see a voltage reading of about 0.616 volts. Let's call it 0.2 volts. So a combination of magnesium and zinc yields 0.6 volts. The next combination I'm going to try is magnesium and copper. So we have copper and magnesium, and we're going to dip the copper electrode into the copper solution and the magnesium electrode into the magnesium solution, connected by a salt bridge, and we can read a voltage of about 1.56, let's call it 1.6 volts. So the combination of magnesium and copper has produced a very, very large voltage relative to the others. Let's try one more. The next combination I will try is aluminum and copper. So if I place the copper electrode in the copper solution and the aluminum electrode in the aluminum solution, we can read a voltage of about 0.66 volts. So this is, again, a very high voltage, relatively speaking. So let's call this 0.64 volts for the aluminum-copper combination. So for the rest of the combination galvanic cells, we're going to present the data to you in data tables. That's the method that is used to construct galvanic cells. So next time you pick up your cell phone or use any device that uses a battery, including your automobile, whether it's a standard automobile or a hybrid automobile, thank chemists for developing these amazing sources of mobile energy. Thank you. So now let us look at the full set of experimental results for the data tables in this experiment. So in procedure 2A1, reactions with HCl, we found with magnesium vigorous release of bubbles, vigorous bubbling, let's say. With aluminum at first, we observed really nothing, no reaction. Later on, after I did the video, I took a piece of aluminum and I cleaned off the surface very well with steel wool, and after doing that, when I put that piece in hydrochloric acid, 1 molar hydrochloric acid, there was also a vigorous reaction. As I mentioned in the video, aluminum forms a very tough, resilient coating of aluminum oxide when exposed to air, which protects the surface, which is why aluminum, despite being a very active metal, remains shiny in air. Zinc had also a vigorous reaction, albeit probably a little bit less vigorous than magnesium. Tin, we observed to have a very moderate or slow reaction. There was some bubbling. Let's say a few bubbles. The bubbles, of course, in all of these cases would be hydrogen gas being released. And copper showed no reaction. So there are the data observations for section 2A1 of the procedures. So the experimental results for section 2A2 of the procedures involves observations of whether the various metals will replace the other various metals from their compounds or from their salts dissolved in water in the so-called single replacement reactions discussed in the experimental write-up. Of course, a metal won't replace itself, so for the zinc on zinc, or aluminum on aluminum, magnesium on magnesium, tin on tin, and, tin on tin and copper on copper. We didn't do those. With zinc and aluminum, I'll use NR to indicate no reaction in this table. So no reaction there. So zinc did not replace aluminum. No reaction with zinc and magnesium. With zinc and copper, we noted a spongy copper formation. That characteristic reddish color of copper was appearing as the zinc was dissolving because the zinc was replacing the copper. And in the case of zinc and tin, we saw some, you couldn't see it very well in the video, some black coating appearing on the zinc, and that black coating was finely divided tin metal that was forming. So zinc was indeed replacing the tin from tin chloride. When we put aluminum into the other solutions of the other metals, we saw that aluminum had a slight reaction with zinc, we really didn't clean off the aluminum well enough to notice a very vigorous reaction, but indeed aluminum should be replacing zinc. Aluminum and magnesium, we observed no reaction. Aluminum and copper, after scraping off the surface of the aluminum, was positive. So again, copper formation, the same as with zinc. We had the reddish colored copper appearing on the surface of the aluminum. And then with aluminum and tin, similarly, a black coating occurred on the piece of aluminum, indicating that there was a reaction occurring and that the aluminum was replacing the tin. With magnesium and zinc, we had a reaction where zinc was formed. So we noticed the magnesium was dissolving and zinc metal in a sort of spongy form was being generated. With magnesium and aluminum, we noticed also a slight reaction. Magnesium should replace aluminum, but it wasn't exactly a vigorous reaction. With magnesium and copper, we had a vigorous reaction. The magnesium was replacing the copper quickly, so we noticed again copper formed, characteristic reddish color, and a spongy copper was formed. And then finally with magnesium and tin, also a vigorous reaction, where tin, again, a blackish colored tin was formed. Tin and zinc, no reaction. Tin and aluminum, no reaction. Tin and magnesium, no reaction. And tin and copper, we really did not observe a reaction, although I'll put parenthetically that it should have occurred, because I know that tin is more reactive than copper. Wasn't really observed here. Copper and zinc, no reaction. Copper and aluminum, no reaction. Copper and magnesium, no reaction. And finally, copper and tin, no reaction. So from these results, one can then generate a scale of activity for these various metals. That is, which metals will replace other metals from their compounds. So in procedure 2B, the construction of galvanic cells, recall that we took two different metal strips, and dipped them into solutions of their respective salts, either nitrates or chlorides, and we connected those two salt solutions with a salt bridge, a piece of filter paper soaked in potassium nitrate, which served to complete the circuit between the voltmeter and the two metal solutions. So for magnesium and aluminum, which I did demonstrate to you, we obtained a voltage reading of 0.42 volts. Note, by the way, that the first metal appearing in the columns here, in each one of these combinations, so magnesium, 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 zinc, etc., the first metal of the pair was connected to the negative pole of the voltmeter. Voltmeter, of course, if you've ever used a voltmeter, has a positive and a negative terminal. So those are little alligator clips drawn very poorly. For magnesium and zinc, so this is one that I did not show you, I got a voltage reading of 0.62 volts. For magnesium and copper, which I did do on the video, we got 1.60 volts. Magnesium and tin, 1.33 volts. For zinc and tin, 0.41 volts. For zinc and aluminum, got 0.45 volts. For aluminum and copper, 0.64 volts. For aluminum and tin, 0.93 volts. And for zinc and copper, 0.51 volts. And finally, for tin and copper, 0.15 volts. So the object of this part of the experiment was to show you that different combinations of metal electrodes will produce different voltages. These voltages that we obtained in this experiment are not exactly what one should obtain theoretically. There are actually theoretical values for these voltages, that are obtained by constructing these various galvanic cells. However, the fact that we constructed them very crudely, using a very crude salt bridge, and using electrodes and connections that may not have been perfectly clean of corrosion, so that the circuits were not exactly just through metal, but also through perhaps some resistive material. The results are not exactly what they should have been, but they give you an idea of how one can vary the metal combinations to produce different galvanic cell voltages, and this is exactly what happens in commercial batteries. So a zinc cadmium battery, or a zinc copper battery, or a nickel cadmium battery, or a lithium ion battery, all of those can produce different voltages because of the combinations of metals that are used as the electrodes. Also, a lead acid battery in your car, of course, produces actually 2 volts per cell, and then there are 6 such cells in the battery itself to produce a total of 12 volts, which is what your car's low voltage electrical system runs on. So that is the experiment electrochemistry. Everybody stay well and stay safe.